Okay, so our poor chap is spending all this time wandering around looking for his wife. But eventually he will find her because he's able to use the sense of smell. And this meeting has had a number of talks about the sense of smell. Chemical ecology, which is a field that I find very fascinating, is becoming of interest to more and more people, and particularly in the vertebrate space, people are moving into that. Little ad from my colleague Ashraf El-Said. Sandy Liebhold mentioned the Ferrobase website, and then there's also the B3 people that Dave Chilon talked about there. So anyway, just a quick ad for those. So invasive species are taking over, and that's what this meeting is about, but we've got this poor chap wandering around. But what would happen if instead of the situation where his wife was the only one with the perfume, if that same smell was everywhere? So he'd be wandering around and he'd be confused and he probably wouldn't find her at that point. And that would be a disruptive technology. And in fact, we've been doing almost exactly that for a number of years. And my colleague Jim Walker is giving a talk a little bit later on from the apple sector, where we're now releasing sterile insects on top of mating disruption. But we've been replacing insecticides with disruptive sex pheromones for apple export pests for some time, and we've got an annual review article that's reviewing this story with Howard Waring, who's our former boss and mentor, and Jim Walker was the lead author on that. So this pheromone technology has enabled us to get away from using broad-spectrum insecticides, which are the organophosphates in the red. You can see we have pretty much phased those out, even in the last millennium mostly, and then those technologies have been replaced by either benign insecticides, much less toxic, much less broad spectrum, or the sex pheromones in a kind of combination. So we have this kind of technology, and we are heading towards this residue-free dream, which is of interest to the apple exporters because obviously they have the premium produce in the market in the UK and Europe and so forth. So that technology is well established, and it doesn't come up every day unless you're working in those sectors. But actually, we have a growing suite of pest disruption tools, and I can't tell you how they came up with this name for 4Play Max. I had nothing to do with it, honest. But anyway, we have this technologies that are out there, and people are adopting them, and they work well enough in competition with the insecticides, which are generally a little bit cheaper. So we have a few hurdles, but actually there's good progress because the technologies are working and people are getting those benefits from that. Now, if we go back to, again, this discussion about eradication of arthropods, so moving it from pest management to the sort of pre-border biosecurity discussion. And this is a slide from a project that we had with Sandy Liebhold, who was earlier in the week speaking, and then Patrick Tobin and others led this particular manuscript. But what we've got there is more or less a J-shaped increase, of course, on a log scale you see there, but J-shaped without the log. And you can see that the number of arthropod responses are going up very, very dramatically. And in fact, we looked at a number of the factors that were important to success, and one of them was this disruptive technology, the sex pheromone coming out for gypsy moth enabled the eradication for gypsy moth to increase very dramatically in success rate and so forth. And in fact, in the course of that analysis, Patrick Tobin hooked out the number 22.7-fold better odds for eradication success when you have an insect attractant. Okay, so that partially explains I guess, why some of the technologies have taken over and become very effective, because they work. And in the end, we can make a comparison between the targets of some of those kinds of organisms, that is to say, the pests either of pest management, as you see in the Ferrobase, sorted out by family there, or on the left by eradication from the Gerda database. And what we're seeing there is quite a lot of the same pest names, the same pest families coming up again and again. So there's a clustering between the pests that people are facing in a pest management sense and the pests that countries like New Zealand are concerned about and will respond to with an eradication response. So there's a lot of overlap in those pest targets. Now, when you get one of those organisms coming into the country, the question is what can you do about it? So under the assumption that you have an attractant, you can put out a trapping program, as was done here in the case of the gumleaf skeletonizer in Auckland. We were able to get the pheromone out of that organism pretty quickly, a couple of months, and 1,500 pheromone traps were put across Auckland, but the insect was galloping across the landscape, as you can see, across the 3 generations at the bottom there. It spread very quickly across the Isthmus of Auckland. And that was in contrast to some of the other organisms that we've been combating over time. The painted apple moth has come up earlier, the full webworm, and also more recently the great white cabbage butterfly. So the rate of spread is a key factor in our ability to respond to these kinds of organisms. Even when we have the pheromone, in a case like this, probably the main benefit for the government was to stand down the eradication. It wasn't going to be feasible to win that one. And we have a similar case actually from California. So this is the light brown apple moth that turned up in California several years ago. And I think Sandy made a comment about the social response to this. But you can see, again, in this case, it was 50,000 pheromone traps, so rather larger budget than we're used to seeing. But so we have the data from 50,000 pheromone traps. What we're looking at there is we're looking west into the Pacific. So you've got San Francisco on the right and Monterey Bay there on the left. So we're looking west, and you can see that the organism has arrived and just colonized the landscape incredibly quickly. Sandy made a comment about the light trap that Jerry Powell actually discovered the light brown apple moth with at his house, and that's the ground zero in this other graph on the right. And you can see over the 3 years the organism moved into Berkeley and just totally colonized that area very, very quickly. So even when we have a pheromone for a surveillance tool, it may or may not be able to support an eradication, just depending upon a whole lot of other factors. So one of the things that we can do, though, is to look at our surveillance programs and think, how can we gain greater efficiencies from them? And so one of the things that we've thought of, and this was a project together with Eki Brockerhoff and some American colleagues in particular, could we put multiple pheromone lures into a single trap? We have a gypsy moth surveillance program in New Zealand. Could we add other species, the pine processionary moth and some of the other things that we really don't want in New Zealand? Could we add those to those lures? Now, one of the problems with that is that often these insects communicate with each other with the same sorts of compounds, and so the pheromone for one species may actually inhibit attraction of another. And it is possible to find, just by screening a whole range of different combinations that actually can give you, for example, 4 species in one trap quite successfully. So there are things that we can do, and this has also more recently been done with fruit flies. So it's an approach that can actually gain some efficiency in surveillance, buying us some time to respond if we can pick up the organism early enough. But let me just helicopter back up a little bit to the sort of chemical ecology concept. Living creatures have odors. There's this chemical language, and you can see there a paper recently illustrating this with the kiwifruit floral volatiles that the honeybee has learned and is actually responding to. Now, in fact, what we found was that the honeybee didn't smell the entire bouquet. Only about 5 compounds out of a much larger number of compounds were actually being detected by that insect. But the point is that odors are diagnostic, and they may be either attractant or repellent. We do have eNose technology, and Andrew Kralachek spoke earlier about this, but I'll give you that diagram on the bottom there where it's about sensitivity. And we don't yet know for Andrew's technology where that's going to be on the line there, but we do see insects, and it's not just bees. You'd also find a number of moths in this parts per quadrillion range of sensitivity on the landscape. Bees may be more sensitive actually than the moths because they share the information. They get a certain amount of leverage. Dogs, which of course cute little dogs like that are being used in biosecurity here in New Zealand and elsewhere, but many of the technologies are less sensitive than dogs, and so we do have a bit of a technology gap between our desire to use diagnostic odors for biosecurity purposes and our ability to actually detect them in a useful kind of way. And so it's an area where there's going to be rapid change, but that's where we stand at the moment. And it's basically about 1 billion times not sensitive enough. So just in the interest of time, I'm just going to hopefully show you another kind of disruptive technology. Hopefully if this movie will work. There we go. So this is the information superhighway. Argentine ants are sharing information, trailing, and harvesting resources until we come along with a disruptive technology. So what's going on there is there's too much information. So the ants can no longer find the edge of the trail and the clean air, and they're crossing back and forth and starting to walk in circles. So we've gone from a situation where there was a good degree of coordination by the insects to one where they're actually unable to harvest resources at all. And we have a recent paper about this where it's coming out on Thursday this week, I think. And the point about that, if you like, the short title for that would be Ants Almost Outwit Scientists. And I guess what I'm saying there is their ability to use a physical cue actually made it more difficult for us to disrupt their behavior. So this is technology which is, I guess, emerging. We're wanting to go from a scenario of the trailing, very coordinated kind of information, right through to something which is more like a Jackson Pollock painting, and where we've completely disrupted their ability to communicate. So this technology is now being commercialized in the US. We're still looking at that here in New Zealand, but actually a company in the US has got a sprayable version of this trail pheromone, and they're putting it out together with insecticides. So we're making progress with these disruptive technologies, but actually they kind of missed the point, I felt, by adding the insecticide in there, but they were able to get it to be quite useful in a commercial sense by doing that. Again, if we drill back down to what's going on with the insects, they're able to detect these odors with very specialized sense organs. Their sensilla have olfactory receptor neurons. Kate Chung Park in the center is doing the electrophysiology, doing olfactory receptor neuron research there on, in this case, Queensland fruit fly, but these other examples are actually from spotted ring Drosophila, so it's another organism that we don't want here. And so we're able to actually detect or determine what sort of odorants these insects can detect, and ideally improve lures so we get greater sensitivity, and ideally also have other techniques for controlling them later on, perhaps a lure and kill or other things like that. Now, you can go from the electrophysiology to the behavior. And here we're back again with the bees, where in this case we've trained honeybees to detect tuberculosis odors. So they're specialized compounds that are coming from these mycobacteria, and some of these odors there, a couple of examples, bees were able to learn at extremely low levels. So there's a potential for bees to be used in this kind of biosecurity space. And in fact, a colleague in the US, Jerry Bromanshank, who has been out to New Zealand a couple of times, has been able to do this based on, I guess, this pollination syndrome that honeybees have and their sensitivity. Now, this curve that you've got there is the standard kind of operating curve that they use in any kind of a sensor, radar, for example. And what's astounding about this is the sensitivity and the correctness of the bee's diagnosis. So they're operating there at way above any other sorts of technologies that have been developed by any engineers so far. And they're using this together with the LiDAR, that's the side-scanning laser system, to localize where the bees are hovering over the landmines on the landscape. So it's a technology which has been proven for quite a number of years. Man-made compounds from the landmines, no problem for the bees to detect those and to learn those, and away they go. It's a disruptive technology, and dogs are still winning that particular war. So it is possible to apply these kinds of technologies to biosecurity questions, and it's something we've been engaged with for some time. However, we, at the moment, don't have the full technology suite that we require. We don't have a telemetry system for the honeybees to be able to localize where they are in the landscape. So while we can demonstrate it at close range, in fact, we can't operate, if you like, in suburbia, where some of the biosecurity problems are likely to be. So let me just finish by saying there's a number of different kinds of technologies that we've put together. In the case of the top left, we have a sprayable moth sex pheromone applied to Mediterranean fruit flies. And so we're using the male fruit fly as a false female, if you like, a false trail, and disrupting that male behavior of the moth in this case. These other technologies, whether it's paintball or these other kinds of ways of deploying the sex pheromones out there in the landscape, all of these technologies are working to an extent, and it would appear to us from the limited work that's been done that they're socially acceptable. However, they're only going to be applicable to a certain number of targets. So we do have a lot of challenges left, and I think at that stage I'll leave it there. Good. Thank you.
Any questions? So, you sort of talk about the limitations of the technology. Do you think that are there ways for us to use new technologies to extend the use of these kind of stereochemical approaches?
I think there are. I think, just to be really out there, really crazy and ambitious, so people have been able to get moths, like silk moths, to drive a car using a trackball and drive up the plume to find where the source is. So if you have a geostabilized unmanned aerial vehicle, why wouldn't you put the bee in the pilot seat? All right, I'll leave it there. Thanks.